orthogonal to the tangent space. Just the normal, I guess. It's learning the normal of this manifold. So that was an interesting interpretation. There you go, like that. Okay, and so you can train these things, and again, here's like noisy versions, and here's the denoised versions. This particular net does a pretty good job. Okay, last variation on this, and then I guess we'll be done. One more strategy for avoiding uninteresting features or uninteresting middle layers is called contractive autoencoders. And so here, same strategy, we're going to add some sort of regularization term. But this one, the idea behind contractive autoencoders is, what we'd like to do is we'd like to figure out which kind of directions of variation in the original image manifold space we care about, and which directions we don't. And so to do that, little definition. So remember that the Frobenius norm of a matrix, so A here is a matrix, Frobenius norm has this F, is just we sum over all of the individual elements of the matrix and square them. Okay, so this is like mean squared error. Just take all the entries of the matrix, square them. And remember that the Jacobian is just the change of the output with respect to the input. So contrastive autoencoders do the following. They say, okay, well, we've got some original loss function, say reconstruction loss, but we're going to add a regularization term. And that regularization term is going to be the Frobenius norm of the Jacobian. Okay, so what is that saying? So we want this to be small. So what does that, how do you get the Frobenius norm of the Jacobian to be small? What does that mean? Yeah.
That is going slowly in a direction that is, in a sense, not learning, because no matter what direction you go, you're kind of small.
Okay, yeah, so you got the right intuition. So when the Jacobian is small, what does that mean?
Gradient's really small.
Gradient's really small, and what does that mean?
Is it not learning?
Is the function steep like this or flat like this? It's flat. So the function is flat. So this is saying we want the entries in the Jacobian to be as small as possible. That means as flat. So we want the function to be as flat as possible. So if lambda is really, really big, what would happen to this loss function?
We try and find a flat function.
I try to find a perfectly flat function. And what would that give you? Would that be good or bad?
We'll give you an optimum.
Well, so I think if lambda is too big, it's going to give you a perfectly flat function, which is just like a constant function. So not good. But somewhere in between lambda really, really big and lambda really, really small, what the network is going to have to figure out is it's going to have to say, well, some entries can be small, other entries are going to be big. And so you can sort of think about the endpoints here. So as lambda is 0, you get just a normal autoencoder that keeps all the information. But as lambda gets big, like it has to throw away information. But the way the network has to balance these trade-offs is to say, I can throw away information in directions I don't care about. And so that's what the network has to learn. So you can sort of imagine that, like there's certain, if you have this manifold of images, there's certain directions which are important. They like control strokes or thicknesses or things like that. But there's other directions that aren't important. And so the contractive autoencoder has to somehow learn that, okay, like my representation, it can go ahead and be super flat in these unimportant directions. Okay. And they actually both work pretty well, so you can use these denoising autoencoders or these contractive autoencoders. They're both awesome. They have some advantages and disadvantages that are complementary. I've heard a lot more recently about denoising autoencoders than contractive autoencoders. And I think that's it. So we did not get to variational anything. So we'll pick this back up again on Wednesday. And we'll see you guys later.